Alright, so the final video in Chapter 8, I know this has been a really big one. This is a big topic, bonding. It is the molecular orbital theory. So this is the third and final bonding model that we're going to talk about, and it's different. I should restate that models are just humans' attempt at rationalizing the physical world that they measure. So all three of those models are valid. None of them are fact. They're just ways that we, with the little we know about science, we sort of build our own understanding of how these things work. And so we have valence bond model, we'll call that VB theory. Um, that's still valid for some things, and it's good for simple geometries, molecular geometries, right? It's really good at describing simple things, and it's simple visualizations. Um, Hybrids or hybridization is really an extension. It's not really a totally different model. It's just a sort of addendum to the valence bond theory model. Remember, valence bond theory just means that you've got two unpaired electrons in different orbitals and they can overlap. And as long as the phases of the orbitals are the same and the spins are opposite, then they overlap and they form a covalent bond. Hybridization, we brought this in because it explained more complex molecular geometries, and we talked about uh, methane, tetrahedral, and things like that. And so we had sp3, sp2, and sp, and this was a better description for that. Uh, Molecular orbital theory, we just call this MO theory often. It gives us a better description of the actual energy levels of electrons and orbitals within a particular molecule. And so it has its own places where it's used and most beneficial. And I'll say in reality, as a chemist, as a practicing chemist, I use all three of these. Depending on the molecule and depending on what model works best and is simplest for definition. I'll say that molecular orbital theory is the one that's probably most advanced and most utilized in actual research. If you go on to Chem 250 and 251, most organic chemists, they don't really ever think about MO theory because it gets complicated pretty fast. And so they're often thinking about big clunky organic molecules and biomolecules. If you take biochemistry, they're using these two models. Inorganic chemists and materials chemists, people that build things like photovoltaics and semiconductors, people like myself, we often use the more advanced theory because we really need to understand what the energies of those electrons are, and that gives us a better model. So let's jump into MO. So with molecular orbitals, they're distinctly different from everything we've talked about before, which were atomic orbitals. So molecular orbitals, as the name implies, those are orbitals that form over the entire molecule. Remember, in valence bond and hybrid orbital theory, all we were doing was taking the existing atomic orbitals that were on individual atoms, say for methane. So if we took the methane molecule, what we did was we took the individual atomic orbitals on carbon, which was specifically the valence, 2s and 2p, and we smashed them together and we made these new sp3 orbitals. But they still were the atomic orbitals for carbon. They had nothing to do with the orbitals for the hydrogens in the periphery. Molecular orbitals, in contrast, take the 1s orbital that's on hydrogen and say the 2s and the 2p orbital on carbon, and they smash those together to form a new orbital, and that orbital actually resides over that entire molecule. In other words, if you remember from our discussion of quantum mechanics, that Greek psi, that wave function, remember, the wave function was the mathematical wave description of where electrons or orbitals are in an atom, and if we squared that, that was the probability function, which is really the shape of the orbital. For molecular orbitals, the math, the wave function, shows the probability over the entire molecule. And this is actually more realistic. The more measurements we do as physical scientists, we learn that electrons aren't simply relegated to an atomic orbital and shared only, say, in the space between the bond. In fact, that electron, quantum mechanically as a wave, is actually residing everywhere in the molecule. And so molecular orbital theory is probably a more accurate description of what's actually happening in a real molecule, which is why it gives us a better picture of the electronic energies of those individual electrons. And there are a lot of similarities with molecular orbitals to the atomic orbitals we've already dealt with, so we don't have to learn an entirely new system. Just like atomic orbitals, remember atomic orbitals, we're talking about things like the s orbital or the p orbital or the d orbital on a specific atom. We learned that those had specific energy levels. That was how we filled them up when we made electron configurations using the Aufbau principle, right? We went 1s, 2s, 2p, etc., from low energy to high. They all have defined shapes. Molecular orbitals, I mean, have defined shapes. So just like atomic orbitals and s had, the specific shapes, molecular orbitals do as well. And finally, we still can only constrain 2 electrons within each of the molecular orbitals that gets formed. In this case, though, the energy and the shape of the molecular orbitals, it depends on the specific molecule. And that's different than atomic orbitals, which all had defined shapes regardless of the molecule. So in this case, we have a little bit more flexibility. So energy and shape of the MO depends on the molecule, and they can get pretty complex pretty fast if you have a complex molecule. So how do we form molecular orbitals? Well, it's pretty similar actually to hybridization in that we're taking 2 atomic orbitals on the 2 different atoms. So let's just say we have our 2 hydrogen atoms here. Those each have a 1s orbital. If we want to form a molecular orbital or set of molecular orbitals for the hydrogen atom from their constituent atomic orbitals, remember these are the atomic orbitals that we're familiar with, we're really just doing a linear combination of those. So there's 2 orbitals that we can form, and that's really key. Just like hybridization, where we could combine 2 orbitals and then the result would be that we'd have 2 new orbitals, the same is true. We have to conserve the number of orbitals. So if we're combining in molecular orbital theory, if we're combining the 2 1s orbitals that comprise the hydrogen atoms, then we're going to get 2 new MOs. Okay, and that's what I'm showing here in this picture here out of the textbook. So the 2 ways that we can form these orbitals are through linear combination, either addition or subtraction of those 2 1s orbitals. So the top picture shows the result of adding, literally just adding the functions of the 2 1s orbitals. So here's a 1s, here's a 1s. We're going to add those together. What do you get when you add them together? You get a bigger orbital. So this is the molecular orbital with those 2 combined, and we're going to call that the bonding molecular orbital. We're going to call that sigma for bonding. And the second type of orbital, remember we have to get 2 orbitals since we're combining 2 atomic orbitals. The second one comes from the subtraction of those 2. So if you're subtracting one phase from another, what you essentially are doing is inverting the phase of the second one, and that's why you get a red going to a blue. And so now it's a similar molecular orbital, but now it's got this node in between. And we call this the sigma star, or the anti-bonding orbital. The second one is going to be higher in energy. Let me show you what this looks like in terms of energy structure. Okay, so I've got the energy diagram started over to the right, and we call this actually an MO diagram. The MO diagram represents energetically which atomic orbitals we're going to combine to form the individual molecular orbitals. And the way that you construct these is you start with the atomic orbital energy levels separated on left and right for the two atoms that you want to bring together. In our example here, we have the simplest of simple cases, which is just hydrogen, or H2. So we have over here on the left, that's the energy level for one of the hydrogens and its 1s orbital. So we're talking about this one here. So just thinking about this is the physical orbital, this is its energy for this atom, for the one on the left. And then similarly, for the other hydrogen atom that we want to bring together, we have its 1s orbital over here. So that is referring to the second 1s orbital of the second hydrogen atom. Okay, so how do we construct the diagram from this sort of this picture? Well, we're adding one and we're subtracting one. We already know that nodal planes in an orbital mean that it has higher energy. Remember, a nodal plane is the point of zero probability. An electron can't reside there. Electrons don't like to have nodes. More nodes mean higher energy because they can't dwell in those places. So if we add two together, what we're going to get is a lower energy orbital down here, and we're going to draw these sort of dotted lines to represent this as one of the new molecular orbitals that's forming from the addition. This is coming from the 1s plus the 1s. So this is this top picture here. And so this here is our sigma bonding orbital. Similarly, this higher energy, we're starting with two atomic orbitals that are perfectly happy, and then we're combining them, but in a subtraction way. We create a new node where one wasn't before. Then, of course, that's going to be higher energy than we even started with. And so we're going to get an energy level up here as well, and that's going to be our second molecular orbital. So this comes from 1s minus 1s, and we're going to call this the sigma star antibonding orbital. And this way of constructing a molecular orbital diagram is the same for really any molecule. Okay, so couple key takeaways. How many atomic orbitals did we start with? Two. We started with the 1s over here and the 1s of the second atom. So these are our two individual hydrogen atoms that we're bringing together. And how many MOs did we create? Two. You always have to conserve the same number of atomic orbitals that you combine in the resulting molecular orbitals that you get. Okay, so the last step that I want to do here is actually think about where the electrons would reside within this new diagram. So the way to think about this molecular orbital diagram is the actual energy levels of the orbitals are just these ones in the center. These are the new molecular orbitals that constitute where electrons can energetically reside in the hydrogen molecule. The two levels on the periphery, those just simply refer to what we started with. They have no bearing anymore. We don't use those. We just leave them there to remind us how or where they came from. So if we think about how many electrons are in a hydrogen atom, well, in each hydrogen atom, remember the electron configuration is just 1s1. So there's just a single electron in each. So we can actually populate in each of our hydrogen atoms, we can start with one electron in each of those. And so those are in the atomic orbitals, but now that we've created these new molecular orbitals in the center here, we just need to populate these two electrons into the new molecule. So we've got two electrons and the Aufbau principle still remains. We start with the lowest energy orbitals and we add our electrons in two at a time, meaning we can fit two in each until we run out. So we've only got two, so we're going to populate them both in this sigma bonding orbital, which is great. And now we know that the actual electronic structure of the hydrogen molecule, this is actually the electronic structure of the hydrogen molecule. We've got two electrons inside of the bonding orbital and 0 in the anti-bonding orbital. And that's the actual molecular picture. Alright, so we clearly need to move to more advanced molecules. We always start with the simplest. So on the left, I've just got a sort of reiteration of what I just drew. So this is the molecular orbital diagram for the simple H2 molecule. So that's what we're looking at here. That's what we just drew, right? We've got the two bonding electrons here in the sigma bonding molecular orbital, and then we've got a vacant sigma star anti-bonding molecular orbital. This is the actual electronic configuration if we're using the molecular orbital bonding model. Okay, So let's jump over here to the right. Here we've got the H2 minus ion. So what's different between H2 and H2 minus? Well, it's just got that extra minus. This is not, for what you'll learn here in a second, it's not a very common ion because it's not super stable. How do we know it's not super stable? Well, let's think about it in terms of molecular orbital theory. If we have the H2 minus ion, that means to start with, looking at our atomic orbitals, right? This is the atomic orbital for one of the hydrogens. This is the atomic orbital for another. If this is H2 minus, that means there's 3 valence electrons that we've got to fill up somehow. We've got 1 over here to start with, but that means we've got 2 over here to start with. And remember, when we have 3 in our atomic orbitals, that means we have 3 to populate in our molecular orbitals. So the only difference in the pictures from left to right is that we get 2 to fill into our sigma, our bonding molecular orbital, but now we have that third one residing in this sigma star. Let's think about what this means, right? Because at this level here, this is essentially the level of 0 energy. Because this is the level of just the atoms by themselves not forming a bond, right? These are sort of the content levels of just the hydrogen atoms. And if you take their electrons and you actually lower the energy of those electrons, that's good. That's net stabilizing, and that's why a bond would form. But if you take some of the electrons and put them down in a lower energy, and then you put some of them up at a higher energy, now that benefit, that energy lowering, is getting canceled out by this energy raising. In which case, this hydrogen ion, the H2 minus ion, is going to be less stable than simply looking at the H2 atom, or the H2 molecule, where it only has 2 electrons that have both been reduced in energy relative to their atomic orbital states. So that's less stable. But we'll say overall this molecule, it's still stable because it has more electrons in a bonding orbital, in a lower orbital energy than what the atomic orbital started at, than in the anti-bonding orbital, right? We've got sort of 2 in there and 1 in here, so we still have 1 electron that's in a lower energy state relative, and that is a net stabilizing force. It's just going to be less stable than the actual H2 molecule. That brings us back to this metric that I'd introduced in a previous video when we were talking about multiple bonds of bond order, and I told you it'd be coming back later, and this is where it becomes really operative. So bond order is a metric to actually assess the stability difference. So a metric for stability. So I just said, you know, sort of qualitatively, well, we've got 2 electrons in the bonding, 0 in the antibonding. Here we've got 2 in the bonding, 1 in the antibonding. So qualitatively, the one on the left, the H2, is going to be more stable. Let's assign an actual sort of semi-quantitative way to do that. That's what the bond order is for. So the bond order is going to be the number of bonding electrons. So how many are in the actual sigma bonding levels, minus the number in the anti-bonding, so the sigma star, over 2. That's what the bond order is going to be here. So let's compute that for these 2 molecules. Let's compute that for H2. That's going to be, let's count this. So we've got 2 in our sigma bonding, and we have 0 in our anti-bonding. Divided by 2, that's going to give us a bond order of 1. And on the H2 minus ion over here, we've got 2 in the sigma bonding minus 1 in the anti-bonding. Divided by 2 gives us 0.5. If you remember from a previous video, we said that the bond order was coincident with what type of bond that was. So if we had a bond order of 1, that constituted a single bond, right? And we said if we had a bond order of 2, that actually meant we had a double bond, a bond order of 3, etc. And so this bond order of 1 is really telling us that there's actually 2 electrons being shared in this bond and nothing else. And that's what we see here. The two bonding orbitals, no anti-bonding orbitals. In contrast, though, over here with the H2 minus ion, we actually have a bond order that's less than 1, meaning we don't even have a full single bond there. And that's because we've got hydrogen here, and we do have 2 bonding, but then we also have 2 in this anti-bonding state, or 1 in this anti-bonding state, which is essentially canceling one of these out and giving us a half of a bond in terms of strength. And so bond order isn't a real thing. It's not telling us whether we have a single or a half or bond. It's really telling us a proxy for the strength of that bond. And it's telling us that the H2 minus has really got about half the strength of an H2 molecule itself, which has got a full single bond. So we need to move away from the really simplistic description of hydrogen and create an MO diagram for a more complicated molecule, and we're not gonna go that complicated. We're gonna stick with diatomics, so 2 atoms, and we're gonna think about first the molecule of nitrogen, N2, and we're gonna draw this one by hand. So let's start by just writing out what the electron configuration for each nitrogen atom would be. So each nitrogen atom would have an electron configuration of closed shell 2s2 2p3. So we're thinking about molecular orbitals, we're only thinking about the valence electrons. We don't care about the core electrons because, as we already know, they don't really participate in bonding. So the process for constructing one of these MO diagrams is first to identify what the valence atomic orbitals are for each of the atoms that are going to be combined to form molecular orbitals, and then drawing them up just as we did on a vertical energy diagram for hydrogen. And so we'll start and we'll put the 2s orbital maybe here. So we'll say that's going to be the 2s, and I should just be explicit here. This is going to be for the first nitrogen atom. So I'll draw 2s, and then I'll draw our 3 2p's. So 1, 2, 3. So those are the 2p's of one of the nitrogen atoms. And then similarly, we'll have the same exact atomic orbital structure for the second nitrogen. So 1, 2, 3 for 2p's. And so these are the individual nitrogen atoms, and these are their atomic orbitals, at least the valence atomic orbitals. And we might as well fill these up to start with. So we know that there's 2s2 is full for each, and then there's 2p3. So Hund's rule, we're going to add 1 to each of those individuals. So just as before, we're going to start by adding 2 s orbitals and subtracting them and getting the 2 new molecular orbitals for just this set. So if we add them together, we're going to get this new bonding orbital down here, and if we subtract them, we're going to get this anti-bonding orbital right here, right? And so I'll draw the dots in just to, the dots don't mean anything except to just remind us where did those molecular orbitals come from, what linear combination of orbitals. So we're going to call this orbital down here sigma, and we're going to call it subscript 2s just to tell us that that's a sigma bonding orbital. Remember, sigma refers to the fact that these are head-on overlap. So let's see if I do this in purple. This is going to be this plus this, these two 1s orbitals. That's what this is referring to. And then the second one is going to be sigma star 2s, because it is the product of the subtraction of the two these are 2s orbitals on nitrogen. Okay, so far no different than hydrogen, but now we've got the 2p atomic orbitals to deal with. Remember, however many atomic orbitals you use to combine to make molecular orbitals, that's how many molecular orbitals you have to have. So in the case of combining these two 2s orbitals, we have now 2 resulting molecular orbitals. If we combine 6 of these p orbitals, that means we're going to have 6 new molecular orbitals. That's exactly what we're going to get. Okay, so I'm going to draw these out. Maybe I'll do this in red just to differentiate the two. So we've got, if we combine 2 of these, they're going to give us 2 orbitals that look like this. They're going to give us 1 orbital that looks like this, and then we're going to have 2 orbitals up here and 1 orbital like this. So we can say, well, maybe we'll say that these 2 come from these outer 2, and I'll show you why here in a second. And this one comes from this one here, and the same is true. I'll sort of loop it up here, doesn't really matter. And these come from this outer 2 here. So again, if you have molecular orbitals that are lower in energy than the atomic orbitals that you started with, then we're going to call those bonding orbitals. And if we have orbitals that are higher in energy than what we started with the atomic orbitals, those are going to be anti-bonding orbitals. So why do we get orbitals that are exactly the same energy in degenerate, and why do we get one that's higher in energy? Well, remember that the p orbitals actually have 3 different orientations. So let's draw those out for a second. Let's be really clear here. So when we write these 3 degenerate orbitals, these p orbitals here, we already know that each of these have their own magnetic quantum number, which means they have 3 different orientations in space. We have one of the p orbitals aligned along the y, one aligned the x, and one aligned the z. And so that's what, when we have these 3 dashes here, what we really mean are these 3 different orientations. Okay, so let's think about how these orbitals actually combine with each other, because really what we have are 2 sets of these orbitals, one from this nitrogen and one from this nitrogen, and all we're going to do is add them together and subtract them, just like we did for the 2 s orbitals here. So let's just look at what that might look like. Okay, so what I've drawn below these orbitals are just sort of simulated pictures of what's really happening when we combine them either through addition or subtraction to create these new 6 orbitals. So for one of the orbitals, one of the new molecular orbitals, that's going to result from the addition of 2 py orbitals, and then that's going to create a bonding orbital, and we also are going to have an antibonding, an equivalent antibonding orbital, or an opposite antibonding orbital through the subtraction. So what's that going to look like? Well, if you add these 2 3-dimensional structures together, what are you going to get? You're going to get something that looks like a little bit bigger than what you started with. And I just drew purple in to show the opposite phase. Okay, so this would be the result of the addition of 2 of the 2 py orbitals. How are these things overlapping? Are they overlapping head-on or side-on? If you look at the addition of these 2 in this orientation, these 2 p orbitals are coming together side to side. And so we're going to call this resulting shape, this new molecular orbital, we're going to call that a pi bond. And we're going to call it a pi bonding orbital. Okay, so let's look at this second one then. That's going to, if we subtract these 2, that's the same as like flipping this second one around and adding it. So what we're going to end up with is something that looks similar, except it's got 2 nodal planes where you've subtracted this, so that becomes a negative, and you've subtracted this, that becomes a negative. And so you end up having 2 nodal planes. So up here you had 1 nodal plane, here you've got 2 nodal planes, which makes this higher energy. And we're going to call this, again, this is a side-on overlap to form this new molecular orbital. We're going to call that a pi star. Okay, so that's the result of just the addition and subtraction of 2 py orbitals to form this new type of molecular orbital. And we're going to say that that is this one right here, this bottom line here. So this is what we call the pi bond, and that's going to result from 2 py's that are coming together. Similarly, then that means this one up here is going to be the sort of opposite pi star, which comes from, we'll just write this as 2 py plus 2 py. This is 2 py minus 2 py up here. Okay? All right, so what about 2px, right? We got to add and then subtract these 2. If we add these two together, what we could get to start with is something that looks like, ooh, wrong color, get something that looks like this, where you've got some bonding and then some anti-bonding, or I'm sorry, two phases here, and then here we'd end up with something that looks like this, where you'd have alternating phases, and again, you're going from 2 nodal planes to 3 nodal planes. But what's the orientation of overlap here? In this case, this is head-on. And since this is head-on overlap, and this is the only one of the 3 actual orbitals that can have the orientation to head-on overlap between the nitrogens, then we're going to call this the sigma bond, and we're going to call this the sigma star bond. And that's the one orbital on its own here, the molecular orbital right here. This is going to be our sigma, which is a combination of 2px plus 2px. And up here we've got sort of the equal and opposite, the sigma 2px minus 2px. Okay, let's look at our final example here then. This example, 2pz, is exactly analogous to the 2py because they're side-on overlap and they're just along a different axis. So we're going to end up with orbitals that look exactly the same, but they're oriented along a different axis as our first case. So that's going to give us something that looks like that for the bonding orbital, and then the anti-bonding orbital is going to look exactly the same as this pi star here with 2 nodal planes, and we're going to call this exactly as you'd expect. This is going to be our pi because these are side-on overlaps. This is pi star, and because they're exactly the same orbitals, they're just pointed along the z-axis instead of the y-axis, they have exactly the same energy, which is why they show up in our molecular orbital diagram as degenerate orbitals. They have exactly the same energy, right? If you look at the energy axis, these two are the same. And so this is going to be, again, a pi, and this will be the result of the addition of two 2pz's, and then we'll have the one here, which will be our pi star anti-bonding, which will result from the subtraction of those 2pz orbitals. Okay, so that fully defines sort of the origin of this. The actual ordering of why we have our pi orbitals here first and our sigma here and then our pi and they're sort of flipped, that's beyond the scope of this class. I'm going to show you 2 different ways that these are written, this way and the other way, that I'll show you in a second. And you're just going to have to know that this is the order that this forms when we combine our 2p type orbitals. So the last thing we can do here then is to fill up all of the electrons within the new molecular orbital diagram, right? This is the new energy diagram for where electron orbitals exist in energy space. So we've got 2, 4 here, so I'm going to go through and I'm going to pop those in. That means it populates both my sigma 2s and my sigma star 2s, so both of those are filled. And now I've got 6 to fill, so I've got 2, 4, 6. Okay, so let's think about then the bond order of this molecule. So the bond order is going to be equal to the number of bonding minus the number of anti-bonding over 2. So let's count the bonding. We'll highlight that in this multicolor. So there's bonding, and then all 3 of these are all bonding. So that gives us a total of 8 in the bonding state, and then only 2 right here are in this sigma star anti-bonding. So this is going to give us a bond order of 3, which, if you remember the Lewis structure for nitrogen, it was exactly that. It had 3 bonds. And so it gives us a pretty good representation of this molecule. So I'm going to walk you through a couple other examples. I'm not going to draw these out. This is the one that I'm going to draw out by hand just so you can see the origin of everything. But I'm going to show you some computer rendered graphics, and I'm going to talk you through what some of the implications of this new bonding model are and our understanding of where the electrons exist. All right, so I've got a couple different molecular orbital diagrams shown to the left. The one on the far left is the one we just drew by hand. That's the nitrogen molecule. And then the ones on the right are actually both oxygen and fluorine. They end up having the same structure, just different number of electrons that fill. And so this is the important point. There's really only two different types of molecular orbital diagrams that we're going to talk about in this class, and these are it. So you can see they look almost identical. The only difference here is the ordering of our sigma 2p and our pi 2p here. Here you can see what we'd shown in the previous case. These two, they go pi and then sigma, but then when you go to oxygen and fluorine, those two switch around. They go sigma pi. So the ordering of these two, that's the only difference between the the two types that you'll see. And so that's any type of diatomic molecule that we would talk about for molecular orbitals in this class. They change over right here on the periodic table. So in fact, carbon and boron, because they're on this side of this line, they also would be they would also have this type of structure. And then oxygen and fluorine, because they're on this side, have this structure that's flipped. But either way, the general idea of just combining atomic orbitals to create new molecular orbitals, it's exactly the same. Exactly the same. The only difference is the ordering of these two here. So the real power in molecular orbital theory, this may feel completely tedious to you at this point, and you're like, well, why do we need this whole new bonding model? I don't really get what the purpose is. Well, for 100 or 200 years, scientists had known that nitrogen and oxygen behaved very differently in the presence of a magnet. And all the previous bonding models, valence bond theory and hybridization, they didn't explain that. So there's something about the electronic structure inside of those different molecules that cause them to behave differently. And so I'm going to show you a video of exactly that experiment that scientists observed, and then we'll talk about the molecular orbital diagrams for each of those molecules and explain why exactly the molecular orbital model explains it. So in this video, this demonstrator has a dewar, which is essentially a thermos, full of liquid oxygen. That's that blue sort of liquid. And what he's going to do is pour it between two poles of a big permanent magnet. And he's going to do the same thing with liquid nitrogen. And you are going to observe what the difference is when you do that. So that's liquid oxygen. There's the big magnet. This is nitrogen. So he's pouring liquid nitrogen between the poles. Notice nothing really happens. It just flows right over the magnets. Nothing changes. Now this is liquid oxygen. Different phenomenon. So the oxygen sticks between the two poles. So there's some interaction with the electrons in that structure, which means they're different electronically. So let's revisit the molecular orbital diagram for nitrogen. We've already drawn this and looked at it a couple times. And let's look at where the electrons are and whether or not there are any unpaired electrons. So if you've got an electron and it's paired, then you've essentially canceled out its sort of impact or its ability to interact with external electric or magnetic fields. We call systems or molecules that have only paired electrons in their molecular orbital structure, we call those diamagnetic. And nitrogen, you can see it only has paired electrons. It's fully diamagnetic, which means it has no interaction with external fields, like that big magnet. In other words, only singly unpaired electrons have the ability to interact with these fields, because once you pair it up, it sort of cancels out the charge of the other, or its ability to interact in a really simplistic way. So we can contrast that now against the oxygen molecule. Remember, once we go from nitrogen to oxygen on the periodic table, the key is that the two orbitals here, the pi and the sigma, those two flip around. And so we have, oh, no, I'm sorry, not these two, and these two. So those two flip around. And if you take oxygen and you fill it up with all of its electrons, what you observe is something really interesting. You've got two unpaired electrons. If you have unpaired electrons in the molecular orbital energy diagram, we call that type of molecule a paramagnetic one. Paramagnetic meaning it does interact with external electric or magnetic fields. And this is the reason why in that video you saw oxygen get stuck between the poles of the magnet, right? It got locked in there, right there, because it had a strong attraction and repulsion force that it was experiencing due to the two unpaired electrons here. This is a big implication because from hybrid orbital and valence bond theories, all electrons were always paired. Everything was always paired. And so hybrid and valence bond theory would predict that every molecule would always be diamagnetic. Everything would be paired. Whereas molecular orbital theory was the first electronic theory that actually predicted the difference in behavior, diamagnetic and paramagnetic. And actually, it's really, really good at predicting these differences in much more complicated molecules than these simple diatomics. And so that's the big utility in molecular orbital theory, is it's very, very, very good at helping us predict the overall electronic structure of molecules. Though it doesn't really tell us that much about the geometry. Right? So hybridization and valence bond theory, VB and hybrid, those are really good at telling us the 3D geometry. Right? That's what we use to help us predict the tetrahedral organization of methane. But MO theory is the best for electronic energies and thinking about things like paramagnetism and diamagnetism. So that's the benefit of MO theory.